The one-time pad, this is a classical cryptography scheme, and in this cryptography, the one-time pad is unbreakable classical encryption technique. It cannot be cracked theoretically and guarantees perfect secrecy, but it requires the use of one single-use pre-shared key that is larger than or equal to the size of the message being shared. Now, pre-shared key that is larger than or equal to the size of the message which you are going to send, it should be both with the receiver, sender and the receiver. Now, one-time pad crypto system, it was first proposed in 1882 years to preserve confidentiality of telegraphic messages. It uses a pre-shared key that its size must be the same as bigger of the message or bigger than the size of the message. And in this scheme, every key is used only once, and that is why it is called as one-time pad. Now, quantum key distribution helps to create these super secret keys which we need for a one-time pad to encrypt messages. So it's like having a super secret code that is extra safe. Because there are several methods, you can even go for head and tail, and sender and receiver, they can just make a secret key. They can decide that secret key like this, and previously they used to decide like this only and using some other methods. But by using quantum cryptography technique, if you are manufacturing, I can say, or if you are creating a secret key and this is being utilized for one-time pad, so then your key is, it is your super secret key which cannot be hacked anytime. Now, key points are that it requires a random key that is at least as long as the message. Not that in particular sequence you should have a key. It can be any random sequence of 0 and 1 and should be as long as the message which is being encrypted, and encrypts by performing a bitwise XOR. So already you have that. Now we are going to use this bitwise XOR operation between the messages, the plain text and the key. And then this ciphertext is sent to the receiver, and the decryption also involves another bitwise XOR key with the same secret key. So this is how we are going to use the one-time pad. And for designing a key, you have to take a sequence of 0101. Actually, most of you must be familiar with this. These are the ASCII codes. There is ASCII code for every character. Whichever you press on your keyboard, for each and every character, there is a ASCII code. And some ASCII codes are assigned to even these characters A to Z. So for simplicity, we have taken these characters. Now, these are the binary codes, 0, 1, 0, 0, 0, 0, 0, 1. These are the binary codes, so you cannot write A in, your machine cannot understand A as A. Only human being can understand A as A. The machine only knows the machine language, which is nothing but a sequence of 0 and 1. So if you are writing this sequence, the first one, and then it will say that there's a character A and so on. Now, because my young participants are there, I would go further just to explain them that how ASCII value will be computed. Here, this is ASCII is American Standard Code for Information Interchange, and for A it is 65. Let's see how. So first of all, you will have to convert your binary number, which we have seen in the table. This was the binary number for A. So it was to the base 2, and convert this into decimal number. So the conversion is very easy. If the binary number is there, then you have to multiply each digit from MSB to LSB with reducing the power of the base number 2. So because there are 8 bits and we always start with 0, so first of all it will be the weightage will be 2 to the power 7. So the 0 will be multiplied by 2 to the power 7, then plus next bit is 1, 1 will be multiplied by 2 to the power 6, then rest of them are 0, so 0 into 2 to the power 5, 4, 3, 2, and the even, okay, 2 to the power 1 is also 0. Then the last will be plus 1, because the bit is 1, this will be multiplied by 2 to the power 0. So 2 to the power 0 is always 1, and 1 multiplied by 1, so the last will be 1, and all others which are being multiplied by 0, they will be 0 only, and the only one is remaining. What is that? 2 to the power 6. So this is 64. So 64 plus 1, that is 65. So this is how the A is represented by 65. In decimal digits, it is 65. The value is that. Now, quick method. Quick method means once you become expert who is going to do all these calculations, we know that once we become matured, then there are methods. So what you can do is the first weightage पे जाना, पहले का 1, then 2, then 2 2s are 4, 4 2s are 8, 8 2s are 16, 32, 64, 128. Now let's compute A का. So where there is 0, you need to worry. बाकी जहाँ जहाँ 1 था, so 1 was at अगर मैं right to left ले रही हूँ, then it is from second, and then the 8th bit is 1. So 64 plus 1, that will be 65. बाकी सब तो 0 है. Now quickly you find the value of what will be the ASCII code of Z.
Binary is 010111010. So if we use the quick method, then from right, so 2, this is 0, so this won't be counted. So 2 into 1, so here we write, this 0 won't be counted. So 2 into 8, 1 into 8, which is 2 raised to 3. So this is 8 here. Then 2 raised to 4, which is 16 here. Then 0, so won't be counted. And 1, so 1 into 64, which is here. Adding it, it is 90. That would be the ASCII value of Z.
Right. Start sending message. And we will use our secret key. We have learned how a secret key can be prepared using BB84 model, and we will be using it here. And this is all assumption that what message we will send, so that we will assume, and we will also assume some secret key, and we will go further. So first of all, suppose the original message is ORG. Okay, so wherever ORG is written, this is your original message, and where key is written, this is your secret key, and where MSG is written, so that message is the message which you are sending, the message which you are sending. So this message will be received. ORG, which can be stored in L-bit register, and let's assume that for simplicity, our L-bit register, it can accommodate, or it can hold 8 bits. So L-bit register is encoded with the use of key KEY, which is also a number between 0 to 2 to the power L minus 1. So why is it 2 to the power L minus 1? Because we are starting with 0, so we are subtracting the first, then 2 to the power. Encoded message is nothing but, what will be the encoded message? We have already seen that what we will do, we will take our original message and we will encrypt it with the help of the secret key. So you will perform XOR operation here for this original with XOR with your key, and the message equals to, XOR key. Now what is message? Message is nothing but the original message XOR key, and again this will be XORed with another key by the receiver. So when it is being XORed, you know that in that day the bits are same, then the value is 0. So 1 will be 1 XOR 1 will be 0, 0 XOR 1, 0 XOR 0 will also be 0. And if they are dissimilar, then only they will result in 1. So same will happen here because the key holds the same values, and if they are XORed, so definitely you are going to get the answer as 0, and therefore you will get the original. Now let's take one example. Let's send a message original to the receiver in binary. And for simplicity, I've taken it as U because U is very nice. Coding is there 01010101. So let us send U to the receiver. Now next slide. The bits are same. Let us send U to the receiver. Now next slide. Now before parting ways, you and your friend, suppose you are sending it to your friend, and then you have agreed on a key, maybe using a coin with heads as 0 and tail as 1 or vice versa, and randomly you have generated a key of the same length as of message, and both have made sure that they have the same key. This is very important. Now here is a twist. Using QKD, both of you have obtained the key instead of using head on tail or any other classical method. You have obtained it using the QKD, that is quantum key distribution method, and by applying BB84 protocol. Now let us assume that our shared key is following. For simplicity, again I have taken it as 11110000, and now perform XOR or exclusive or operation between message was
Original message was 01010101.
yes,
That is
and
U.
key was ORG.
11110000.
Right. Now you compute.
As these two are different, they will be 1. As these two are same, the XOR will be 0. These two are different, so 1. These two are same, so 0. These two are same, so 0. These two are different, so 1. These two are same, so 0. And these two are different, so 1.
Okay. Now this ciphered text we will send to our friend. Okay. Now I have written Bob. Now assume Bob is your friend. So send it to Bob. Now at Bob's end or your friend's end, the decoding will be done. You have encrypted and decryption will take place. You have done encoding. It will be decoded there. So how will it be decoded? The message will again the same key will be applied. Same key will be applied. Then apply it. The message received was 101000101, and our key is 11110000. Now again perform this.
These two are same, so it will be 0. These two are different, so it will be 1. These two are same, so it will be 0. These two are different, so 1. Same, so 0. Different, so 1. Same, so 0. And different, so 1.
So what is this 01010101? This will be the message received by your friend. And what will be it? It
It
will be
is the
it
original
is
message.
you. The original message you. So this is how the one-time pad is used along with the quantum cryptography, the key generated by quantum cryptography method. Now next, now let us see what is the eavesdropper, what eavesdropper will do. Now eavesdropper is there, but suppose the name of they have taken it. EVE is the name given by the model, those who have designed the model. Now it tries to eavesdrop and to measure each of the Alice photon. But the moment she tries to confirm, suppose she has measured all of them instead of Bob, she has carried out everything and she has everything in hand. But as soon as she tries to confirm it with Alice, she will get exposed, right? And the next photons, they have Heisenberg uncertainty principle, that photons will get destroyed once they are measured or they are tempered. So, because of that, once it hits a detector, the photon will no longer exist, and whichever the Eve will try to detect, so they will get destroyed, and Bob will receive less photons as was expected. So, as per expectation, it is assumed that at least 25% of transmitted photons, because we have not talked about them because it will confuse while understanding the methodology, but few of the photons will definitely will get destroyed because of the uh, environment and the noise and all that. So 25% of the total transmitted photons must reach to the Bob. So if we get less traffic, then definitely he will guess that something is wrong in the system, and this is how they will throw and will go for creating another one. So why quantum cryptography is secured, we have discussed it very nicely. I think now it is very clear because of these two properties provided by the quantum mechanics. We The quantum cryptography is totally, it gives a secured method for for sending our messages in a very safe way. Now, next slide. Now, let us summarize. So, first of all, I would like you to read all the three slides one by one, and after that, I will proceed further. So, please be attentive and just try to understand each and everything and see if you have understood it or not. All the young participants, please read them very carefully and very attentively. So, I'm giving you some time, and as soon as you finish this slide, please give a green signal in chat so that Dhanil will go to next slide. Dhanil, next slide. So, uh, there was a question that how both will get the same key. So, what is this is what we were doing with that methodology. It is only because for um, designing a key, for preparing a key which is known to Alice and Bob and no one else. So that method is just for that purpose only. So yes. Now okay. Next. Okay. So because the world is expecting, anticipating that the quantum computers, they are capable of breaking traditional encryption, and therefore the demand for quantum safe solutions like quantum cryptography is set to skyrocket. Because even when quantum computers will be there, even that time the classical computers will also be there, and then the key generated using quantum cryptography methodology will provide the solution to the classical computers to keep themselves safe from the attack from even from the quantum computers. And for that the post quantum cryptography is there. So latest research area is that. And quantum cryptography, because the principles of quantum mechanics are being utilized here instead of mathematics, so it holds immense potential for revolution, for changing the various aspects of our daily lives, and it is still in the early stage of development and deployment that we have already discussed. So there are several real world applications where we do need quantum cryptography to be explored and implemented. So let's go through a few of them. The secure communication networks. So all new applications such as quantum digital signatures will come, and quantum secret sharing and quantum voting So they can enhance the functionality and trustworthiness of all the cryptographic protocols. Now on this platform, I have already written, but I have one novel idea. Uh, I have a dream that we should have quantum voting booths in future. We can have, and as and when the voter press the key, the vote should get deposited and recorded in the database at the central servers through 100% secured communication network. And then the results will get declared very next morning, because quantum computers will be handling all the tasks. So they are so very fast that the next day morning all the results can be declared. Looks achievable with quantum computing because it offers tremendous speed and it also offers 100% security. So we can dream. Financial institutions, there is sensitive data and secure transactions should take place. So definitely their financial services, their quantum cryptography will play a major role. And data centers and cloud computing, they handle vast amount of data, and it can play a significant role there also to secure all these infrastructures. And then the Internet of Things. Now, Internet of Things, IoT devices, they raises concern regarding their security to cyber attacks. The quantum cryptography offers a potential solution by providing a secure key distribution and encryption mechanisms for IoT devices. With quantum resistant algorithms, secure communication channels, the integrity and confidentiality of IoT data, it can be preserved, uh, saving us from potential risk. Then in defense, of course, in defense, the quantum cryptography, it can enhance the government and defense organizations capabilities by enabling the secure transmission of classified information, protecting the military information communications, which are of vital importance, and they are very critical and they should be totally secured. So the integrity of critical infrastructure can be ensured using quantum cryptography. Healthcare and medical data, there also there is a vast application of quantum cryptography, because the sensitive patient's information, medical records, there is a need for additional layer of security to be provided for protecting electronic health records. And then it can enhance the authentication and identify management systems also. So the query is that, is it already in end user's hand? Quantum cryptography is still in early stage of development and not widely available to end users in its purest form, but the technology is primarily being researched and tested by academic institutions, government organizations, and selected industry players. You know who are they? First day we came to know about all that. So, however, there have been some limited deployment of quantum cryptography and certain applications, but it is not yet accessible for average end user. It is still evolving and there are challenges to address. So which are the challenges? The technical complexity, because it requires specialized infrastructure and these systems are currently expensive and not easily scalable. Quantum computing development, researchers are actively working on I've already informed you, that they are working on post quantum cryptography, which focuses on developing encryption methods that can withstand attacks on classical computers from quantum computers. And infrastructures and standards, this is again a challenging factor. Establishing infrastructure and standardized protocols for quantum cryptography is essential for its widespread adoption and to ensure compatibility between different quantum cryptography systems. So that is also there. to worry about or to be taken care about. And then integrating quantum cryptography with existing communication systems, it can be challenging. It requires modifications to existing infrastructure protocols to accommodate the unique feature of quantum cryptography, and the education and awareness, which is the most important, and we people are there for it. Quantum cryptography is highly specialized field, and there is a need for education and awareness among professionals, decision makers, and users. And despite of the fact that quantum key protocols are theoretically well structured and designed, their real implementation has certain imperfections. This is human error, defective optical fibers, unwell constructed detectors, and other loopholes becomes the cause of attacks that are performed against QKD schemes. So there are various challenges that appear and are subject of research. But despite these challenges, the future outlook for quantum cryptography is definitely promising. And there is lot of scope for young generation to get into it and become pioneer in this particular field of quantum computing. And for that, what basically is needed, your math should be sound, and if you are very good in physics and computer science, then world is all yours. So with that, I end my session, and the references are there. Thank you. Thank you for.
Thank you so much, Dr. Haba, for such a lucid representation. You touched upon distinction between the classical to the quantum cryptography, moving on to polarization states which are required for the bits. And then you talked about the case studies, like how these are actually done, along with the utility of the keys which are there. And then you also talked about different other examples and applications and challenges. I think this session has also provided another, say, understanding of a very difficult topic otherwise. There are some questions in the chat which I would be reading, and in that case, please keep on answering that. Vinayak says, ma'am, is it anti-diagonal? What is anti-diagonal polarization? I assume, Vinayak, by now you must have understood, because ma'am, after you had written this question, ma'am had explained again also. Ma'am, please, you can tell the answer otherwise.
If you want to understand it like this, the qubits are either in one of the two eigenstates of either rectilinear 0 or 90 degrees, or diagonal 45 or 135 degrees. So if you do not like the word anti-diagonal, it can be 135, because if it is measured from 0, then 45 is your, in diagonal case, it is 1, and then the anti-diagonal will be at 135. So that
says, what is difference between a photon and a polarized photon? What does polarization do to a photon?
I think you should answer this. Why we are polarizing a photon? Because we want to align them in particular specific direction. So for that purpose, that is the difference. Now, if polarized means all possible directions, but if it is polarized in one particular, like if you are sending it through vertical filter, then the state will be vertical only. So it will be in one particular direction, and then only you will be able to, or the computer scientist thought like this, and then they can assign some eigen value to eigen state. Eigen state is there, but then if we can maintain this state, then only the value can be assigned. So then it is 1. It can be assumed as 1, and then the horizontal can be assumed as 0. So that's
Ma'am, may
why.
I request you to send the quiz link, because it is being
Yes,
asked
sir,
in the
yeah.
chat
Someone
meanwhile, so that
has,
participants can start doing it.
yeah.
And
Please do it. I've already, yeah, he shared it. I had sent
yes,
it him so that they can, yeah, all
okay,
others
thank you.
can.
Yeah, it has been shared by Dhanil, so please all of you can attempt doing the quiz meanwhile. I must also tell that for the participants that polarizers are used in order to create different polarization states. These are polarizing sheets which can be used to create a particular type of polarization. So those who are from the physics background can also read about that how different polarization states are created. Now, next question is this is, I think, like a comment by Germany only. Are we inscribing data into photons to transfer information? So I think you are saying it right. Next question is, what if photons, ma'am, please say,
Yeah. What is?
what if the photons get mixed up while traveling? The information passed would then become something like an anagram to solve.
If they get mixed up. Yes, coherence is one aspect that it is the ability of quantum system to maintain a superposition of states without collapsing into a single state through interaction with its environment. So if they get interacted, then they will collapse, and then they will be no more in quantum state, they will be in classical state. So this property is crucial for performing quantum computation because quantum algorithms rely on manipulating and processing information encoded in quantum states. And when a quantum system loses coherence, then it undergoes decoherence, meaning it becomes more like a classical system with well defined states.
There was a comment by now, Professor Aluwalia ji, to please say about the session, and then this can be handed over back to the organizers. Thank you. Thank you so much.
Thank you, Vandanji, and thank you, Professor Abha. Thank you very much. I think you have done a very tough job today, and because it was packaged in a very small time frame, so the participants will have to really work hard to appreciate each and every step which you have explained to them. I think you brought in very nicely the what you call examples that how Alice and Bob communicate with each other, and the complete quantum process was explained. I think that was the key element of this. It was for the first time that Alice and Bob appeared in our seminar. But Alice and Bob are two very important, communicators who make this look like a game, which is very difficult to appreciate right in the very beginning. And that is what has been the reason that people have been saying that quantum computation and quantum information and quantum cryptography, they are very, very tough fields. For a audience which is drawn from physics background, I think it is a wonderful first exposure which you have given. I must say that. And the way you had brought out various references for the participants to follow in future, I think that should be a great, great help. Thank you very much. You added a new dimension. Rather, today we have jumped over to what you can call the application of quantum computation in a very interesting and important field at which everybody is actually trying to gain upper hand, whether it is uh, countries like India or countries like USA or China. There is a very tough competition around. So thank you very much, Abhaji, once again. I think you are one of the key members of the group who has curated this course. So I have nothing else to say, but say that big thank you for you. Thank you.
Thank you.
Thank you
Thank-
so much, sir. Thank you so much. And thank you, Abhaji. I hand over to Dr. Madhusudan. Thank you so much.
Thank you, Vandana ma'am, for hosting this wonderful session, Quantum Cryptography. I would like to thank you, Abhaji, for enlightening the audience on the topic quantum cryptography. So as it is already 8:15, with few words I would like to conclude.